Thank you very much, Jochen, and it's a great pleasure for me to chair this first half of the afternoon session, which is dedicated to charge transport in organic semiconductors. And we have two excellent speakers, and the first one is Vitaly Pozdorov from Rutgers, who is one of the pioneers in studying charge transport, in particular in molecular crystals. Vitaly, over to you.
Thank you very much, Henning, for your introduction. Well, first of all, I would like to thank the organizers for their invitation. This is a very interesting workshop and I'm really enjoying these days. So today I wanted to tell you about our recent high-resolution AC Halleffect measurements of organic semiconductors that helped us to understand, to obtain a much improved understanding of some features in charge transport in these materials. This is, by the way, a photograph of a rubrin crystal with a field effect transistor structure deposited on it. This is our favorite system, sort of like a fruit fly of charge transport studies in organic semiconductors. Okay, so this is an introductory slide showing some very simple basic idea of Hall effect. You probably know that originally Hall effect measurements in organic semiconductors were carried out in these high performance rubrin single crystalline transistors. And what we do here is we run current between source and drain. So the charge carriers are flowing in this direction, and the magnetic field is applied perpendicular to the conducting channel. And there is a Lorentz force acting sideways on the carriers and causing their trajectories to bend toward one side of the channel. And that produces this Hall voltage measured across the channel of this perpendicular direction, perpendicular to the transport. And this is what is being measured in this experiment. So the importance of the Hall effect measurements is that they really help you to distinguish the bend-like transport from incoherent hopping. Because in the case of a band transport, there is a microscopic velocity of the carrier here. And I hope you can see my pointer. So that the Lorentz force is non-zero and you see a Hall effect. As opposed to this situation, in purely hopping transport, charge carriers are moving by hopping from molecule to molecule, which is the process of quantum mechanical tunneling. So even though in this mode you have non-zero current flowing in a certain direction, microscopically you don't have velocity. So you have basically tunneling probability between molecules. And at least the classical Lorentz force in this case is zero, and you shouldn't be observing any Hall effect in this case. So just the observation of the classical semiconductor-like Hall effect in these systems is already a smoking gun proof that the charge carriers are delocalized and the transport can be bend-like. But also, since in most of the cases Hall effect probes the instantaneously delocalized mobile carriers, the mobility that you extract by using these measurements gives you the intrinsic upper limit, the band mobility of the system. So that's another benefit of the Hall effect. Now, the problem with Hall effect measurements in organic semiconductors is that they are very difficult to perform because the signal to noise ratio is very poor. This slide shows a few examples, and you can see that in most of these cases, the noise is really high, even though measurements are done here in pretty high magnetic field, 6 Tesla here, 10 Tesla, 10 Tesla, 6 Teslas. And the reason for this is simply because the mobilities are relatively low compared to inorganic counterparts. But also we have trap and release processes that contribute to these fluctuations in noise. So the signal to noise ratio is usually pretty poor. And in order to solve this problem, we have recently developed this AC Hall measurement methodology, which is based on the known principle of phase sensitive detection. So in this case, we apply instead of a DC magnetic field, we're applying a small low frequency AC magnetic field and detect the whole voltage using a lock-in amplifier tuned into this very exact frequency. And so this method really boosts your signal to noise ratio. So the magnetic field in our system is generated by mechanical rotation of this assembly of permanent magnets. So the sample is sitting here in this, this is actually a narrow flat vacuum chamber. So the sample is seeing an alternating magnetic field as these magnets rotate. So this methodology significantly boosted our signal to noise ratio. So here I listed some good features of this setup. So now we can resolve Hall effect in many low mobility systems, and I list some of them here. But also what is important is that the system uses small magnetic field. The magnetic field here in our case is less than 1/4 of a Tesla. And we don't need any superconducting magnets. We don't need liquid helium and so on. It's a small convenient setup. And recently we have upgraded it so that we can do temperature variable measurements. We can do photoexcitation in situ while measuring Hall effect. We can do strain measurements and so on. So here I'm showing a couple of examples of these measurements. So on the left, these are measurements of high performance single crystal rubrin transistor. You can see that as transistors, these devices work very nicely. Nice linear characteristics in the linear regime, perfectly parabolic characteristics in the saturation regime. In this panel C, you can see that mobility measured by different methods, 2-probe, 4-probe, and by Hall effect, they match pretty well. Also, here you can see that the capacitively defined carrier density, shown by thin solid line, matches pretty well with the actually measured by Hall effect carrier density, these dots. Actually, when the Hall measurements and FET measurements coincide, we call this situation a fully developed Hall effect, indicating that 100% of your charge carriers are delocalized, are band carriers. On the right here, I'm showing an example of another type of system. This is a relatively low mobility system. It's a single crystalline tetrasync transistors. You can see that overall level of mobilities here is below 1. It's more than 10 times lower. Nevertheless, this high resolution method allowed us to measure Hall effect in this system. And this was initially a surprise, one of the mysteries of the Hall effect, that we actually see apparently a fully coherent Hall effect here. You can see that Hall mobility matches the longitudinal mobility, and carrier densities are matching too. Well, the reason this was a mystery, because it was believed that when the mobility is below 1, system should not be exhibiting band-like transport at all. It should be a hopping system. Nevertheless, we see a fully coherent Hall effect. At some point, we were able to explain this mystery by developing this model. Let me just briefly mention this here because I actually wanted to focus on other things more in this talk. So the main idea here is that, well, we follow our gurus, Alessandro Troisi and Simone Frattini, who taught us that even in the best organic semiconductor, where the system is very pure and you don't have any static disorder, you still have off-diagonal thermal disorder due to the thermal motion of the molecules. And this thermal disorder produces these tail states. These are the localized states that exist next to the extended band of states. And so when you pour in the charges into such a system, you feel all the states to a certain level, and you would always have a coexistence of carriers that exist in the band. These are the band-like carriers, and also carriers that are moving in the shallow states, in the localized states, the hopping carriers. So if you consider the coexistence of these band carriers that are shown here schematically by the red dot and hopping carriers, you would come to a conclusion that even though the band carriers, they do experience Lorentz force and electric forces, the hopping carriers, they only experience the electric forces, but no Lorentz force. And so the whole electric field produced by the band carriers would be pushing the hopping carriers in the opposite direction, and they would compete with the band carriers in the development of the whole voltage, causing a partial, at least partial compensation of this whole voltage. So when you work out the details of this model and analyze it, we actually came to the conclusion, and we showed this in this paper, that this model successfully captures many interesting features of the Halleffect in organic semiconductors, including explaining some of the mysteries. In particular, in this case, in the case of tetrazine transistors, the model shows that there is a large parameter space here, where you can be pretty far away from having 100% of your carriers band-like. Nevertheless, the hole mobility and FET mobility would be different by a very small amount, within 10%. So the system sort of pretends like being fully coherent, but it's not. There are also other mysteries that the model successfully captures. I will not go into details here, but just very brief, a brief mention here is the Takea's result showing underdeveloped Halleffect in pentacene. Also, these results on Halleffect measurements from the Henning groups that measure Halleffect in the systems and the temperature dependencies. These can be explained with the model. Okay, so now let me switch gears to some new studies. We recently used this powerful technique, AC Hall technique, to address the question of intrinsic mobility strain dependence in organic semiconductor, in rubrin specifically. Well, by intrinsic here, I mean the reversible changes in the mobility caused by applying elastic strain. So to do this, we use these devices where a very thin rubrin crystal is laminated on a flexible substrate, and it's coated with a parylene, which is a very good gate insulator, and topped with the gate. The thickness of the crystals in our device is somewhere between 100 and 300 nanometers usually. We can apply uniaxial strain, controllable uniaxial strain in perpendicular directions in this plane. So we use this notation where the B-axis is the high mobility axis and A-axis is the low mobility axis in rubrin. The strain is applied by using this miniature strain stage with a calibrated mechanical screw. So you can bend the substrate in a controllable way. So we essentially do FET and hole measurements simultaneously under strain. So this slide shows the main results. So the top panel here is the mobility as a function of strain epsilon in %. So the negative values correspond to the compressive strain, positive values correspond to the tensile strain. These symbols, red and blue, are the data for the strain applied along the transport direction. The transport direction in these devices is along the high mobility axis, along the B-axis. The strain here is applied along the same axis, and you can see that there is a large effect of strain when it is applied along the molecular slip stack. But when you apply strain in the perpendicular direction, which is shown here by these darker data points, there's almost no effect on the carrier mobility. By the way, the lower panel here shows essentially the same data set, but what is plotted on the vertical axis is the relative mobility change, delta mu divided by the unstrained value of the mobility. There is a little bit of a lag here in terms of this plateau looking region. We believe this is some sort of a device artifact. Probably some small amount of strain, initial strain, is accommodated, absorbed by the elastomer before it really is getting, before the substrate is transmitting strain into the crystal. So this causes, there's a little bit of a threshold here, but that's okay. We can live with that because the rest of the dependence is quasi-linear. So you can see that the effect of strain is anisotropic and is actually quite large in this experiment. It corresponds to about 70% of boost in mobility when you apply 1% of compressive strain. To be fair, I have to mention that there are other people who try to address this dependence. We're not the first ones. There is the Badlock's preprint, it's online. And there's also a paper by Michaela Mata and co-workers. Apparently, these are very nice early attempts, the pioneering attempts to address this very challenging problem, showing some interesting data. But unfortunately, I cannot compare too well their data with ours because there are certain experimental deficiencies here. And I just wanted to briefly mention a few of them. So first of all, everything in this works is done by two probe measurements. And as we know, for instance, from this recent work from Dan Frisby group, contact resistance could be strain dependent in organic devices. And so one needs to account somehow measure contact resistance also. Otherwise, these could cause some artifacts. No measurements were done under compressive strain applied along the transport direction. Actually, in the second paper, no compressive strain at all was applied, which is very strange because this seems to be the most interesting part. So these data are missing. No Halleffect measurements were done. And the strain effects were done in a very narrow range of parameter space. So if you overlay the data from this paper on our data, you could see you will see this. So all of their data would be within a very small range of tensile strains, and these points here, these colorful circles, show the maximum values. Well, so essentially, I can say that their data are inconsistent with ours. They're simply too limited for a good high quality comparison. Also, there is already a good body of a theoretical effort in this direction to model this dependence. So there are currently 4 papers with the most recent one from Johan's group, published just a few days before this workshop. So this is very interesting. But unfortunately, we don't have agreement between these theoretical predictions and our data. And currently, we don't actually understand why. It could be one of two things, or both. First, there could be some missing ingredient of the model that that prevents us from getting this agreement. Or alternatively, there could be something that we don't really understand in our experiment. Although I can't imagine what at this moment, because we seem to be addressing this problem from multiple experimental perspective. But anyway, so the current state in this part of the field is that mobility strain relationship is still an open question. And we're actually planning to do more measurements in this direction. And I hope the theoretical effort will continue to. Okay, so let me now switch gears again and talk a little bit about Halleffect in high quality polycrystalline organic transistors. So in this project, we collaborated with Antopoulos group. They are growing these nice films based on blends. They blend C8-BTBT with conjugated polymer, which sometimes they dope with this molecule for improved performance. And the small molecule film crystallizes, it phase segregates and crystallizes on top, and you get this nice polycrystalline films. So we complete them with the transistor structure and measure Halleffect. And also we collaborated in this project with Barry Rand's group at Princeton. So Barry is growing absolutely magnificent polycrystalline rubrin thin films. They have this huge grain size. I've seen up to 1 millimeter. They're compact. They are large area. Visually, they are completely transparent on a substrate. They can grow these on solid substrate or flexible substrates. And their performance is approaching actually almost getting to the performance of single crystalline rubrin. Also, fundamentally, this system is interesting because the grain size is so large and the grain boundaries are so well defined that you can have a single grain or just a couple of few grains in the macroscopic channel of your device. This is actually a photograph here, a polarized optical microscope image of one of these devices. You can see that the grains are nucleating from this point, and doing polarized optical microscopy, you can actually determine the exact crystallographic orientation of each grain. So you know what type of grain boundaries are there, what angle, and you can look at the transport and Hall effect as a function of whatever grain boundaries you have in your channel. So this is what we have done in this paper in some of the studies. And one of the interesting results was this. So it's shown here. So you can see that the behavior of these polycrystalline field effect devices is pretty good. You have nice characteristics. You have a rather high linear regime FET mobility here. This is longitudinal mobility, about 6. These are some of the best numbers. But every time we do Hall effect measurements in these devices, we see much lower field effect much lower Hall mobilities. In this case, 3 times lower. And this cannot be explained by that model that I mentioned earlier, by saying that, oh, there must be a lot of hopping carriers in the system that are screening your band carriers. This doesn't work because in that model, at this kind of level of mobilities of 6, transport should be 100% delocalized. I mean, 100% band carriers. And so we start thinking in terms of grain boundaries, and we came up with this model that seems to be able to explain this. So this cartoon here shows the channel. The vertical direction here, the X direction, is the longitudinal source drain direction. And when you have grains here, each grain works like a single crystal, which is misaligned. So all these grains, they have different orientation, and there might be some anisotropy of the charge transport within each grain. And so you are generating a Lorentz force or Hall effect EMF, electromotive force, in each grain. And the value of this Lorentz force is different because it's proportional to the longitudinal mobility mu x. But mu x for each grain is different because the grains are misaligned, while the source drain field, this EX, is the same for each grain. So therefore, you need to be able to balance exactly, if in the steady state, each of these Lorentz forces that are different in each grain by the transverse electric field. Okay, so in the case of a homogeneous channel, you have just one value for the electric field defined by the excess charges accumulated on the edges of the channel. But in this case, you cannot do it by one value. So in order to be able to balance the Lorentz force in every grain at the same time, you have to be something that carries a charge sitting between your grains. And so by this logic, we came to a conclusion that the grain boundaries must be capacitively charged under the Hall effect measurement condition in this case. So that when you go from left to right, every time you cross the grain boundary, there would be a small potential drop associated with that grain boundary. And when you have many grain boundaries between the Hall probes, this would accumulate, and cause a partial reduction of or screening of the Hall voltage. So overall, I think this would be important to understand this this mechanism, because for practical reasons, every time you need to characterize practical, which means polycrystalline thin films with Hall effect measurements, we better to keep this in mind, this mechanism. Finally, let me switch gears one more time and tell you about our recent another experiment. This is the first, to my knowledge, photo Hall effect measurement in organic semiconductors. Again, here we used our powerful AC Hall technique, and we used our favorite system, rubrin. These devices are not transistors, so there's no gate dielectric or gate. So we have just a crystal, freestanding crystal with a free surface with a Hall bar contact. in a whole bar contact geometry. And instead of relying on charge injection from contacts, in this case, we generate carriers by light. So the sample is illuminated uniformly with light, and you generate electrons and holes. These electrons and holes drift in the opposite direction along the channel, and in principle, both of these type of carriers should be contributing to the photoconductivity and the photo-Hall effect. So we have developed a model that assumes that you are generating equal concentrations of mobile electrons and holes, and the model is actually the details of the model is described. The model is described here in this paper. So the model shows that basically in conventional semiconductor, the photo-Hall mobility that you are measuring in such an experiment should be showing the following dependence on the photocarrier density, photoexcited carrier density. Well, the horizontal axis here, you can think about it as incident light intensity. So it should exhibit this roll-off, and at high intensities, photo-Hall mobility should be flattening out at a saturated value, where the photo-Hall mobility value should be equal to the difference between the mobility of electrons and holes. So mu electron minus mu hole. And the reason this happens is because in the limit of low light or in the dark, you are measuring the mobility of majority carriers that existed even before photoexcitation. Those are, for instance, unintentionally doped holes or electrons. But then as you generate more and more photocarriers, they become dominant, they become dominating the photoconductivity process. And at very high photoexcitation, they completely dominate, and electrons and holes in this measurement, they compete in the formation of photo-Hall voltage. Therefore, you're supposed to see the difference in mobilities. We have done some control measurements in single crystalline silicon, and we do see this roll-off. This black curve is the photo-Hall mobility. By fitting this dependence with the model, you can extract actually separately both mobility of electrons and holes. So the model works, but when we do this measurement in rubrin, we see something completely different. So here is the plot showing the photo-Hall mobility measured in high quality rubrin crystal, the black data points, and you can see that this is flat. It's flat. There's no roll off. Okay, and this is happening over many orders of magnitude. So we covered here 7 orders of magnitude, and it's completely flat. By the way, another benefit of Halleffect is that you can tell the sign of the charge carriers. You can see whether holes or electrons are dominating your process. And in this case, the sign of the carriers are holes. So this whole situation looks like all the electrons that we might be generating, they're trapped. They're completely trapped, and 100% of photocurrent is carried by holes. So we're generating only mobile holes under photoexcitation. Also, we directly measured from these photo-Hall measurements the photogenerated carrier density. This is the way it depends on the incident light intensity. You can see a power law dependence with this fractional power close to 1/4. Sometimes in some samples we see 1/3, a little bit of a lower quality. In high quality samples we only see one quarter, always see 1/4 power dependence. And this is consistent with one of our previous work, where actually published in this by Irkin, where we studied photoconductivity as a function of excitation intensities. And that's where we first observed these interesting unconventional fractional power exponents. And they were explained by the model we developed there based on triplet exciton diffusion, interaction of triplet excitons with surfaces, with mobile carriers, and triplet fusion. This is what seems to be causing these power exponents. So here, this essentially is, we confirm this result by a completely different measurement. Now this is photo-Hall effect. looking directly at the photocarrier density. So apparently what is happening, this is our new understanding.
Vitaly, you need to come to a conclusion.
Okay, sure. So basically the conclusion here is that the triplet excitons reach the surface and interact with electron traps. Electron is trapped, the hole is released. That's how photoconductivity is generated here. Okay, so this is my conclusion. I hope I was able to show you that AC methodology is AC hole methodology is very powerful. You can address a range of interesting problems. Please feel free to visit our webpage for many interesting details. And here I thank the people involved, Yarjan Chen, Hyung-Ho Choi, and Vladimir Bruyevich, who contributed to these topics that I covered. And I am really grateful to all these wonderful people, my collaborators, specifically Barry Rand, Thomas Antopoulos, and Jun Takeya on this project. And we are financially supported by the US National Science Foundation. And thank you very much for your attention.
Thank you, Vitaly, for a fantastic talk. Unfortunately, we don't have time for discussion now, but I would suggest that you can meet Vitaly on GatherTown later. And if you have any questions, or use the Slack channel to ask him questions.